Hi everyone, my name is Samantha Chetty and I'm a student at the University of KwaZulu-Natal. Today I'm going to be giving a talk on paleoclimate. According to our hierarchy of models, we are now on number 4, which consists of drifting continents, climate change, and ice ages. In the beginning, the galaxy came into existence with a Big Bang. We start off a model Earth with a bare rock and learned that the distance from the Sun alone was not enough to explain the temperature on Earth. We then learned that a static atmosphere and ocean made the Earth too hot. Thereafter, we added the moving atmosphere and ocean into our model, which provided a much better representation of our climate. Lastly, we learned that all models are wrong, but some are useful. Before we dive into what causes paleoclimate change, we first need to know what paleoclimate is and the importance thereof. Once we understand these concepts, we can then explore the methods that enable us to date and determine past climate. Earth's climate has changed over millions of years. We've experienced climates so extreme and warm that we had rainforests where we now have ice sheets in high latitudes. On the other hand, Earth had turned so cold that it was actually referred to as snowball Earth. Are you intrigued? How did organisms survive these drastic fluctuations in temperature? Was the Earth always habitable? Let's learn some more on this fascinating topic. So back to basics. What is the difference between climate and weather? Weather can be described as the state of the atmosphere, for example, rainfall and temperature, at a specific moment in time. Climate is the average weather conditions over a long period of time. So what is paleoclimate? Paleo means old or ancient. So paleoclimate means the study of climate or geological past. It is important to understand that our past climate gives us insight into past conditions, such as sea level change, ice coverage, and carbon dioxide concentrations. As future climate change can have major impacts on the Earth and the human population, a good understanding of the processes of the past and how it links to climate change is imperative to help us understand what to expect in future. This is a very useful graph which showcases the change in temperature throughout geological time. The x-axis represents the years before present, while the y-axis represents temperature. We can see there's a very distinct line that separates approximately 3 million years ago to the period before that. From 3 million years ago up until present, we notice these cyclical changes in Earth's temperature. The peaks and valleys in the graph refer to glacial or ice ages and interglacial or warm periods. So what may have caused these periodic changes? Milutin and Milankovitch proposed that the drastic changes in Earth's temperature were influenced by the Earth's movements. The underlying understanding behind that is that the Earth's position is that when the Earth's position changes in relation to the Sun, we can assume that the amount of insolation or sunlight received also changes, which impacts temperature. Milankovitch cycles refer to 3 main astronomical factors of importance, all occurring in a cyclical manner. These are eccentricity, obliquity, and precession, occurring in cycles of 96,000, 21,000, and 40,000 years respectively. We know that the Earth orbits the Sun. The shape of the Earth's orbit varies from nearly circular to mildly elliptical. Therefore, eccentricity measures the variation in the shape of the Earth's orbit, which determines the length of the seasons. So in layman's terms, we move from the shape of a donut to the Indian treat, a gulab jamun. Earth's axis isn't straight, but at a 23.4 degree angle. This results in us having different seasons like summer and winter. So obliquity describes the change in the degree of the tilt of the axis, which ranges between 22.1 and 24.5 degrees. Precession describes the direction of the Earth's axis of rotation relative to the stars. It does not point towards a fixed direction in the sky. Instead, the axis of rotation moves in a clockwise circle through space, similar to that of a wobbling top. This is a realistic representation which shows us the change in tilt, shape of orbit, and the direction of the Earth's axis of rotation. Now that we understand what may have caused these ice ages and warm periods, we can further ask ourselves, how did scientists know these dramatic changes occurred? Reliable global climate records are only available from the 1980s. Climate proxies are preserved physical characteristics of the past that stand in for direct meteorological measurements. You can think of climate proxies as nature's record keepers that come in the form of trees and stalagmites, to name a few. Because we can't go back in time to see how hot or cold the climate actually was, how much CO2 was in the atmosphere, we rely heavily on climate proxies to reconstruct past climate. Here are more examples of climate proxies, for example, ice cores, corals, and tree rings. The rate of growth and deposition of proxy material is influenced by the climatic conditions at the time that they were grown or deposited. Some proxies, such as gas bubbles trapped in ice cores, enable traces of the ancient atmosphere to be recovered and measured directly. It's pretty much like a time machine into the past. Another example of a very useful proxy is pollen. Pollen grains are tiny, yellowish, reproductive bodies of seed pods. What makes them really fascinating and useful is that each genus of species has unique morphological characteristics, such as shape, which makes them easy to identify. Furthermore, different plant species grow in a certain climatic niche, which enables us to reconstruct past climate using our understanding of modern distributions. Here's pollen at a range of magnifications. It's pretty, right? When pollen is blown away into bodies of water, such as lakes, the tough outer wall allows them to be preserved in sediment layers. To make use of this proxy, scientists extract a well-dated sediment core from these regions. We can see the years here. After analysis of the sediment core, you can create a pollen diagram like this one, which shows you the change in the percentage of different plant taxa with depth. Trees like black spruce are especially useful because they only grow in taiga or snow forests in high latitudes. So if we find black spruce pollen in old rocks near the equator, we can then infer that the Earth may have been colder during that period, as the equator tends to be quite hot. Remember, the present is the key to the past. Despite pollen being a great proxy for paleo-environmental change, long-term pollen records in Africa are very sparse. Why? Because much of Africa is too arid to support the preservation of microfossils, such as pollen, in suitable archives like lakes. Given these preservational challenges in Africa, paleoscientists have turned to alternative proxies. An example of a uniquely African proxy is Hyrax middens. So what are Hyrax middens? Essentially, Hyrax middens are communal dusty toilets which are found in sheltered rock crevices. They are characterized by a strong smell, accumulation of fecal pellets, and a brown tar-like urinary product called Hericium. When fresh urine flows across the midden, it dries and crystallizes in these layers. Samples are taken and analyzed for multiple proxies, hence the term multi-proxy. This allows for direct comparison of many proxies along with radiocarbon dates, which you'll learn about soon. Hyrax middens also provide us with phytoliths, microcharcoal, and pollen evidence. Microcharcoal remains gives us insight into past fire regimes. What's even cooler is that Harrick's methods provide evidence in the form of lipid biomarkers, ancient DNA, and stable isotope analysis, which is indicative of hydrological and vegetation change. Very useful. Now that we know the drivers behind paleoclimate changes and the methods used to determine the change, we can ask ourselves, how did scientists know when these changes occurred? Luckily, none of our scientific dating methods involve catfishing. Similar to real-life dating and online dating, there are two specific types of scientific dating. Relative dating is a comparative approach to dating. It basically uses a sequence. Essentially, relative dating is more like ordering instead of actual dating. In contrast, absolute dating methods provide us with the exact age of objects, for example, rocks. Ages are determined using radiometric dating, also known as radioactive dating. For relative dating, we look at the sequence of layers, in this case rocks, and we assume that the youngest rock layers at the top are at the top, and the oldest layers at the bottom. This is called the law of superposition. On the other hand, with absolute dating, we know the exact ages of these layers. A commonly used example of absolute dating methods is radiocarbon dating. Radiocarbon dating is a process whereby an object is dated by measuring the ratio of carbon-12 to carbon-14. Before I explain this process, we need to know that carbon-12 is stable and carbon-14 is radioactive. Carbon-14 decays at a known rate into carbon-12. Cosmic rays, or high-energy particles, bombard the Earth's atmosphere and creates unstable carbon-14. The carbon-14 in the atmosphere forms carbon dioxide and enters the global carbon cycle via photosynthesis. Now it's taking the same amount of carbon-14 and carbon-12, which is carried up the food chain. When organisms die, they stop exchanging carbon with the environment, and the carbon-14 content starts decreasing. Over a long period of time, carbon-14 decays into carbon-12, with a half-life of 5,730 years. By calculating the missing amount of carbon-14, we can determine how long it took to lose that amount, and thus we can date the sample. Just like romantic dating requires caution, we have to do the same in scientific dating. I have a few tips for you. Know your limits. Certain dating methods only give accurate ages within a certain range. For example, amino acid dating can't date samples younger than 1,000 years old. Dating is hard. It can be tricky, especially when it comes to dating radiocarbon samples post the year 1700. It's okay to be a sugar daddy or sugar mama. You can accurately date samples that are millions or billions of years old. You can use uranium-lead dating just to make sure that your samples are very, very, very old. Anything older than 1,000,000 years will do. Speaking of age, South Africa has a fossil site that dates back to 5.2 million years ago. The fossil site of Longabaanvlek is located in the West Coast Fossil Park, which is approximately 150 kilometers north of Cape Town. It is world-renowned for its exceptionally well-preserved fossil remains. What's really special about Longabaanvlek fossils is that they provide a portal to the period prior to recurrent ice ages. Consequently, the site places us in the perfect position to study a major global climatic shift from the South African perspective. This enables us to reconstruct what conditions were like during a warmer Earth, thus enabling us to prepare for projected change in future. Now that you listened to my story, we know that the Earth has undergone various extreme climatic changes over billions of years. These changes are caused by megabit cycles and other natural forces. Proxies are extremely useful as they record the change in climate, while radiometric dating assists us in creating a timeline of events. This understanding is essential because paleoclimate studies will help us to predict and prepare for future scenarios. Lastly, we know that migratory cycles are responsible for the last 3 million years worth of climatic changes. But what caused the interesting climatic changes before that? To answer this question, we need to take a look at the next interesting topic, which is plate tectonics.